So why we are very, very excited about the sampling distribution? Because when you know the sampling distribution, you know the properties of your sampling distribution, you are able to tell, once you select a sample randomly from the sampling from the population, that when you get a mean from that sample, you'll be able to tell the probability of how close this sample mean, all right, how close the sample mean is to your population mean. And you can see now the relation with inferential statistics, right? Because what we want to find, after all, when we don't know the population mean, we simply want to estimate it. And when we learn in this topic that when we collect a sample from a population and we get the X bar of that, we know that this X bar belongs to a probability distribution that has specific properties. Okay, we can tell how close we are from a population mean. Okay, we're going to do that. We're going to do that in the next few steps. But I need you to really grab now this notion of sampling distribution. Let's see first the form of the distribution itself. So let's say we got these 500 X bars. Remember that we showed in a table. Let's say that we do a histogram out of it, and you are familiar of how to build a histogram. And why it's important, because when you build the histogram, you are able to tell what shape of the distribution is. Okay, so let's see it. Here is the histogram that we built from the table of 500 values of X bar. So take a minute to observe that and tell me, what does it look like? So please just pause the video and really spend some time to observe it, come out with your own observation. All right, so what did you observe? Let's see if you got it correct. First, we can see that here we have our familiar bell shape, right? It's a bell-shaped curve or form. Look at this. I hope that this will work well with my mouse. Okay, not bad, not bad. Okay. All right, so it looks like a bell, right? So it has a bell shape. And what else? We can see that we have a large, in fact, the largest concentration of the values of X bar. You can see that here, if you want three big, the highest columns, they are where? They are around the population mean, right? Which we know that it was, I think, 52,300. This is very important for us, right? Because what we can see here is that it seems this mean, okay, of the population is also the mean of the distribution of the X bars, right? This is a distribution of X bar now, not X's. This is a very important observation, and we're going to use that. So this is now if you want, the formal definition of sampling distribution. Okay, it's the probability distribution of all possible values of a sample mean X bar. Okay, all the possible values of X bar. So as we learned so far in the previous topics, that any distribution has properties, right? And the three most important properties are the expected value, the standard deviation, and the form. Very important. So for the form, we have already some hints about the form, right, from the previous slide, and also for the expected mean. And we're going to see what about the standard deviation. But in order to describe that distribution, describe that sampling distribution specifically, we need to see what about these three properties. So let's observe these three properties. So the first one is about the expected value of these X bars. Okay, so like any variable, X bar has so many variables. We have seen 500 of these, right? We are always interested, whenever you have a variable, you're interested in its central location, right? So we're interested here in the mean of these values of X bars, right? So what's that? We call it the expected value of X bar. Remember, we used to, for example, the expected value of x, we used to call it E of x or mu. So now we have mu of x bar or E of x bar, right? Very simple. And that's it. We're going to use either this notation, mu of x bar, and this, or E of x bar, and mu of x bar, as we have seen in the histogram, is nothing but equal to the mean of the population. So this is the first property that we know about the sampling distribution. Okay, so the mean of x bar, or the distribution of x bar, is equal to mu, okay, which is the population mean. Now, what about the standard deviation? We can see here that the standard deviation, we call it sigma of x bar, all right? We have two cases. If we have a finite population, so it's a countable number of values, okay, then we're going to use the first equation. Otherwise, if we have an infinite, so meaning that very large population, then sigma of x bar is a simple it's a simple function of sigma, which is the population of the standard deviation of the population itself, sigma. Okay, we divide that by square root of n, where n is the sample size. So we can see this term here, we can see it on the top, but we are multiplying it by this, which we call it the finite population correction factor. Okay, where capital N is the population size. In most of our cases, we're going to use that simple one, okay, which assume an infinite population, or the population size is that large compared to the sample size that we can assume that one. Okay, so now we know about the mean of the distribution of x bar and the standard deviation of this distribution. So let's see what we can get more. Okay, so when the population size is small, when the sample size is small compared to the population size, then the correction factor would be close to 1. Okay, and that's why in this case we're going to use also that simple form, okay, to find sigma of x bar. So this form is going to be sigma x bar in two cases: either when the population is infinite, meaning that very large population, or even in the case of a finite population. However, when capital N, the population size, is much larger than small n, which is sample size, what's the criterion for much? It's greater than 20 times n. Okay, in these two cases, then we're going to use that simple relationship between sigma x bar and sigma. Now, there is a specific name for sigma x bar. We call that the standard error of the mean. Okay, this is only the name for that, but what's important is to know how to find that, and mainly we're going to find it always using that simple form. So let's see in the example, in our EAI example, what would be the sigma x bar if we collect a sample of 30. Okay, we know that the population standard deviation is 4,000. Remember that we found that at the beginning of these slides. Now, let's see if we're going to use which format to use for sigma x bar. We know that we have a finite population because we are looking for a list of 2,500 managers, right? So it's finite, where n is 2,500, sorry. Let's compare that to 20n. So 2,500 is much larger than 20 times 30, which is only 600. And that's why we can then use that simple form, and sigma x bar would be equal to sigma over square root of n. Sigma is 4,000 and n is 30. It's our choice. We decide on the sample size. So for us, it's equal to 30 here, which means that the standard deviation of the distribution of X bar is equal to 730. Okay, you can see that it's much lower than the standard deviation of the population. And from your normal, okay, I'm not going to say more words here. Let me wait a little bit. What's still missing for us to describe completely the sampling distribution is the form of that distribution. So we know that E of X bar is equal to mu, sigma of X bar is sigma over square root of n in most cases, but what about the form? To find the form, we're going to refer to the central limit theorem. What does that theorem say? That the sampling distribution of a mean collected from a population, if this sample is sufficiently large, then the distribution of the sample mean is approximately normal. And the larger the sample size, the closer the form of the sampling distribution will be to the normal distribution. So you may wonder then how large it should be so that we can say, yes, it is normal distribution. There's a general practice here, general understanding among statisticians, that a mean as large as 30, then it gives us some confidence that the sampling distribution would be normally distributed. So for us, for any sample size which is 30 and above, then we are comfortable to say that the sampling distribution has a normal distribution. All right. So what are we saying now as a conclusion here for all what we have seen? If we know that X is normally distributed with a mean of mu and standard deviation of sigma, then when we collect an X bar from that population, X bar belongs to a distribution called X bar, okay, which is also normally distributed with a mean also of mu and standard deviation sigma of X bar, which is equal to sigma over square root of n. All right, this relationship is very important, and we'll learn later that when we don't know about the population itself, we're going backward. So we know about X bar and we're going to make an inference about X. So I'm going to show you the inference process in the next slide. This will be finishing up this discussion about sampling distribution. So how does the sampling distribution help me in making inference about the population? So we know in the inference process, what do? We select a sample, we find a sample mean, and this sample mean would be an estimate for the population mean, right? As we discussed before. However, we know for sure that this sample mean, that specific sample, would not necessarily lead to a mean equal exactly to the population mean. There is always a difference. We know that and we accept that. However, we're going to use our knowledge for the characteristic or the properties of the sampling distribution in order to make some probability statements about how different is that sample mean is away from the population mean. And this will be our method of inference. Okay, we're going to do an example that illustrates that process.